Hello dear students, welcome to BYJU'S exam prep. So guys, in today's session, excuse me, we will discuss about the sedimentation analysis. So basically guys, from this particular part, you also may get the question in the GATE examination and in the ESC examination also. Because if you are able to understand the sedimentation analysis, then you are able to solve the problem which is related to the sedimentation tank, and it is related to the grid chamber also, because this particular concept is to be useful in both the cases, whether you are learning the water supply engineering and wastewater engineering. So in this session guys, I will explain the complete derivation part of the sediment settling velocity of a particle, and which particular velocity we have to use in different condition, whether it is a laminar flow, turbulent flow and transition flow, and how these velocity will vary. We will discuss about it. Okay, so let's understand this particular topic guys. Okay, so before starting the session, let me introduce myself also. My name is Krishna Yadav and I am teaching from last 9 years, and I have done my masters from IIT Roorkee guys. I have mentored almost 20,000 students for the various examination like GATE and ESC, and generally the subjects in which I deal is environmental engineering, structure, RCC and engineering mechanics. So guys, we have one more session which is basically free GATE workshop. If you want to join it guys, you can join it today at 8 p.m. right? So let's understand the theory part of the sedimentation analysis first. What is basically the principle behind the sedimentation process, right? That we have to discuss first. Okay guys, so let me explain it in detail. Excuse me. Listen guys, let us suppose if this is a sedimentation tank, okay, or let us suppose this is a container, excuse me, in which I have some water, okay, and let us suppose guys, in this particular water some sediments are present. Okay sir, now the question is whether these sediment will settle down into the tank or not. The first question is that. Now if the specific gravity of these particles is greater than the specific gravity of water, then only these particles will settle down, otherwise it is not. Correct? So can I say that guys, the first thing of the sedimentation is if the particle specific gravity is greater than 1, or you can say that the density of particle should be greater than the density of water, then only the particle will settle into the tank, otherwise it is not. But we know that guys, good evening Lavan, good evening guys, come fast. Okay, we know that there are two type of matter which can be present in the water. One is your organic matter and the second is inorganic matter, which may be present in the water. Now what are the sources of these type of matter? Inorganic matter are nothing as basically the silt and sand particle which is present into the soil, and they may come with the flooding of the water or flooding condition right inside the river. So guys, we can say that there are two type of organic matter, there are two type of matter which may be present in the water or in the river water. Basically it is inorganic matter and the organic matter. Inorganic matter and the organic matter. Now guys, if we talk about the inorganic matter, the specific gravity of it is 2.65, which is greater than 1. Then definitely this type of particle can settle down into the water because it have density greater than water density. Similarly, if you talk about the organic matter, the specific gravity of it is basically 1.2 to 1.4. So again, this particular particle will also have the density of organic matter is greater than the density of water. So again, we can consider both the type of matter can settle down into the water, but it also depends upon the size of particle. Right now you are able to understand the particle can settle, but the question is if the size is bigger, then it will settle down quickly. If the size is smaller, then it will take a lot of time to settle into the chamber, right, or in the water body. And that's why we need to understand the sedimentation process. Okay, now guys, if we talk about the time duration or let us understand first thing, which is basically the sedimentation tank in simple. In river water, we know that guys, the sediments are flowing with the water itself. But our task is to remove that particular particle in our water treatment plant by using sedimentation tank. So the chamber or the tank which you are using to settle down these type of particle is known as settling tank, or it is known as sedimentation tank, or it is also known as sedimentation basin or clarifier. Clear? And the second thing is that the time required to settle down this particular particle into the sedimentation tank, that is to be known as what? Detention period. That is to be known as what? Detention period or settling duration. Clear? I think you are able to understand these 2 points. Now we need to understand what are the factors due to which the sedimentation process may get affected in our sedimentation tank, and how we can change that particular parameter so that we can increase the efficiency of sedimentation. Okay, let's understand one by one. So the first thing is velocity of flow. Velocity of flow. Let's understand with one example. Guys, you can see here, let us suppose this is a river, correct? Now, in this particular river, if the velocity of flow will be more, then I can say that guys, the turbulence will be more. The turbulence of water will be more. If you have more turbulence in the water, so tell me guys, whether the particle will settle down into the riverbed or not. You can say that guys, no sir. It is not possible to remove all the particles when we have a very high turbulence. Why? Because due to the turbulence or due to the very high flow velocity, these particles are trying to travel with the water itself. And that is the reason guys, due to which the particles are not able to settle down at the riverbed level. Clear? Okay. So how we can change this particular turbulence, or how we can reduce this particular turbulence in our sedimentation process, that we have to understand, right? So guys, in general, I have told you that if the velocity of flow is more, then it increase the turbulence, and if it increase the turbulence, then the sedimentation efficiency will be lesser. Now how I can change it? Very easy to understand. Listen guys, in this particular case, you have certain cross-section area, right? Whatever cross-section area of river is there, let us consider AC. Now guys, let us suppose this is a channel through which water is coming to the sedimentation tank. The water is coming to the sedimentation tank. Now guys, you can see here, this is the area of cross-section, this area. You can see here guys, this area which is available at this particular location. So this is the area of cross-section which is available through which the discharge of water is coming, correct? Let us suppose this is the discharge of water. Let me draw it so that you can understand in detail. Let us suppose this is nothing as, this is basically discharge of water. So this discharge of water is entering into this particular cross-section area of sedimentation tank. Now what is this area, sir? Let me explain. This is nothing as, this is your length of the tank along which the flow will occur. That means the flow is to be like this. This is basically width of the tank, and this is nothing as our height of the tank. Now you can see here guys, the cross-section area is nothing as, basically it is B into H. Now tell me guys, if I change this particular cross-section area, then the flow velocity will get changed or not? Tell me guys. If you change the cross-section area, then the flow velocity will get changed or not? Yes or no? Quickly tell me guys, quickly. If you change the cross-section area, then the flow velocity will get changed or not? Yes, definitely. Yes, definitely. So you can see here guys, in this particular case, our task is to increase this particular cross-section area. If we increase the cross-section area, then Q by AC is equal to what? Velocity of flow. So if you increase this particular cross-section area, then the velocity of flow will get reduced. If velocity of flow is reducing, that means turbulence is reducing. If turbulence is reducing, that means sedimentation efficiency will get increased. So that is one of the approach by which we can control the sedimentation efficiency in our water treatment plant. Are you getting this particular point? It is clear to all of you or not? Tell me, guys. Lavan, it is clear, I think so, right? Okay, very nice. Now let's understand the next parameter, which is nothing as shape and the size of particle. Guys, the next parameter is shape and size of particle. If we talk about shape, so in general, the shape of the particle can be a spherical or it can be a random shape also, right? But at the time of analysis, we are considering the shape of particle as a spherical. Now the question is, why we are considering the particle as a spherical? Because it will cause a lesser drag force, right? If the shape of particle is spherical, then it causes less drag force. Less drag force, right? Less drag force. That's why we are considering the shape of particle as a spherical. Now if we talk about size of particle, tell me guys, if I give you two conditions. Let us suppose this is your sedimentation tank. This is one of the particle whose size is D1 and this is another particle whose size is D2. Now tell me guys, D1 is greater than D2, okay? D1 is greater than D2. Tell me guys, which particular particle is capable to settle down first, whether the bigger one or smaller one? Quickly respond. D1. So definitely if the size of particle is larger, then it can settle down. I am not well, but no issue. We'll continue the session. The topic complete. D1. So you can see here guys, this D1 size of particle can settle down early as compared to D2. Right? So can I say that whatever time is required for D1 size of particle, it is lesser as compared to size of particle, which is basically D2. Correct? So it means if you have more size of particle or the size of particle is larger, then the settling velocity will be more. If settling velocity will be more, so can I say that sedimentation efficiency will be more? Correct? Now tell me guys, are you able to control the shape of particle in the treatment plant? And are you able to control the size of particle into the treatment? Tell me guys quickly. Are you able to control the shape of particle? It is possible to me to control the shape of particle in the treatment plant? Tell me guys quickly. No, it is not possible to control the shape of particle because we are not building it, right? We are not building it. So that's why guys, we are not able to control the shape of particle, right? But if we talk about the size of particle, so if we talk about size of particle, we can control the size of particle by using coagulation. Do you know that guys, there is one of the treatment process in your water treatment plant which is known as coagulation. So coagulation is nothing as it is the process by which we are trying to add it, that means coagulant, into the water so that it can react with the alkalinity part and it will give us some gelatinous PPT. Right? What happened actually? Let me explain. So guys, how we can change the size of particle? Let me explain. Let us suppose if you have smaller size of particle like this, right? So right now the settling velocity of these particles are very less because of size is smaller. Now I want to make a bigger size of particle by combining all of them. How I can do it? So you need to add some coagulant. You need to add some coagulant. Now this particular coagulant, if you add it into the water, then this particular coagulant is trying to react with the alkalinity part. It is trying to react with the alkalinity part. When this coagulant will react with the alkalinity, then ultimately it will give you some gelatinous PPT. That means sticky PPT. Sticky, insoluble PPT. Sticky PPT. Now on this particular sticky PPT, what will happen, guys? You will have some sticky PPT. On this particular PPT, these particles will try to attach themselves, and ultimately the size of particle will get changed. And you can understand, guys, if the size of particle will get increased, so the sedimentation efficiency will also get increased. Understood? So are we able to change the size of particle? Yes, we can control it in our treatment. Correct? The next thing is viscosity of fluid. Now let me ask you one very simple thing, guys. Let us suppose in one container we are filling water, and in second container it is honey, right? Now let us suppose, guys, in both the container, if I put the same size of particle, right, tell me in which particular container the particle will settle down first one or second one? Tell me, guys, quickly, in which particular container the particle will settle first container or second container? Definitely first container. Why? Because we know that, guys, in this particular case water is there, and in water it is easy to flow a particle inside it. But if you have honey, which is a little bit thicker as well as more viscous, right, so that's why we can say that, guys, in that case it is very difficult to move a particle inside it. Correct? So that's why, guys, the viscosity of fluid is another property which may affect the sedimentation process. So the viscosity, generally we are trying to represent it by dynamic viscosity, which is nothing as mu. Correct? So if you have more viscosity of fluid, then the sedimentation efficiency will be what? Lesser. If you have lesser viscosity of fluid, that means it is easy to flow. That means in that case sedimentation efficiency will be more. Clear? So these are the 3 points, guys, which we need to control. But in actual condition, tell me, guys, whether we are able to control the viscosity of any fluid or not. Yes, we can control it by using temperature. But if you increase the temperature inside the water treatment plant for the water, then it is very costly as well as it is very uneconomical for us. Because we know that, guys, if we increase the temperature of a very large quantity of water, then again we have to cool it down. So that's why such type of parameters should not be controlled in WTP. And that's why, guys, you need to understand the size of particle we are trying to control by giving some coagulation process, right? And we can control by, we can change the velocity of flow by providing the larger cross section area. So that's why, guys, these two parameters we can control in the sedimentation part, but this one we are not trying to control in our WTP. Crystal clear? Now, the question is, okay, sir, I am able to understand this particular point. What are the different parameters which may cause some effect on the sedimentation process? Now, the question is, sir, what should be the settling velocity of a particle and how we can derive it? Let's understand in detail. And guys, this particular expression is very useful while understanding the sedimentation tank, grit chamber, and etc. Right? So that's why please remember this particular derivation as well as the formula which we are getting at the last. Okay, listen. Let us suppose if we consider a spherical particle. On this particular spherical particle is present inside a water container. Okay. Now I want to find out what should be the value of settling velocity in this case. And this settling velocity, which is we are considering, it is basically constant. That means this particle is trying to move with a constant velocity inside the tank. Clear? Now what are the various forces which is applied? Listen. First is self-weight, which is nothing as Fw. Fw is self-weight of particle. Second is drag force, which is nothing as FD. Now, when this particular particle is trying to settle down at the bottom, so a drag force is to be applied opposite to the direction of motion. So this is nothing as FD, which is nothing as drag force. Similarly, guys, this particular particle is completely submerged into the water. That's why buoyant force is also applicable, right? So FB is nothing as buoyant force. Buoyant force. Now the question is, what are the values of it, sir, and how we can derive this particular relation? Listen, guys. First of all, you need to understand, as per Newton's second law, the rate of change of linear momentum is equal to summation of forces, correct? Now tell me, guys, if you have mass which is also constant for this particular particle, so during sedimentation the mass is not changing, during settling the velocity is also not changing, it is constant. If you are considering this particular thing, can I say that the summation of forces should be in y direction should be equal to 0? Let me show you that, guys. As per Newton's second law, can I write here, guys, as per second law of Newton, can we write here, guys, the rate of change of linear momentum is equal to what? Summation of forces, right? Now tell me, guys, in this case the mass is changing? No, sir. Velocity is changing? No, sir. So let's take the derivative so that you can understand it. So can I write here, guys, one, we will consider the mass is constant and the velocity is changing. In the second derivative, we will consider velocity is constant and mass is changing. But in this particular case, the mass is also constant and the velocity is also constant. That's why this particular parameter will become 0 and this is also 0. And that's why, guys, we can write here summation of forces is always equal to 0 when you have setting velocity is equal to what? Constant. Clear? Now, if such situation is there, guys, if such situation is there, so it is easy to write summation Fy is equal to 0 in this case. So can I write here Fw minus Fd minus Fb is equal to what? It should be equal to 0. So Fw is equal to Fd plus Fb. Correct? Now, guys, we need to write down the values of sulfate, drag force and the buoyant force. How much it is, that we need to understand. Let us suppose the size of particle is small d, and let us consider the specific gravity of the particle is capital G. Okay, sir. So let's understand it. Just a second, guys, just a second. Just a second. Okay, now you can see here, guys, this is the formula, correct? Now you can see here Fw is equal to what? Fd plus Fb. Now what is the value of Fd, sir? That is nothing as self-weight of the particle. Now what is the self-weight of particle? Specific weight of particle multiplied by the volume of the particle, which is nothing as Vs, right? Now in this case Vs we are writing like this, okay? This is not the settling velocity. That means volume of particle. So specific weight of the particle multiplied by 4 by 3 pi r cube, that means d by 2 whole cube. This will be the self-weight of particle, correct? This will be the self-weight of particle. Okay, now what about drag force, sir? How much drag force will be there? So the formula for drag force is half rho into v. Wait a second, क्या हो रहा है? Okay, That's okay. Half CD rho W into AD square. Clear? AV square. Clear? Now guys, listen carefully. In this particular case, this is the drag force which we have to apply over this particular particle. Over this particular particle. Not what is basically A, sir. What is basically A? This is nothing as Vs square. That means settling velocity of particle. Now what is A? A is nothing as basically your projected area. Right? Now how much it is? I will explain it. Let us suppose this is your spherical particle. If you project this particular area on a plane, then it look like a circle. Then it look like a circle. Correct? It look like a circle. Whose dia is equal to how much? Whose dia is nothing as basically small d. Clear? So this particular projected area you can write here guys, pi by 4 into d square. Clear? Okay sir. The next thing is basically your buoyant weight. So buoyant force is equal to how much? We can write here guys the weight of water which is displaced by that particular object which is present in the water itself. That is nothing as buoyant force. So you can write here gamma W into volume of solid particle. So gamma W into 4 by 3 pi d by 2 whole cube. Clear? So this is one of the expression. This is another expression which is nothing as FD, and this is another expression guys which is basically our FW. Now we need to equate all three of them to get the final equation. Clear? Let's do it. So FW, gamma W multiply by 4 by 3 pi d by 2 whole cube is equal to half CD rho W AV square, right, plus buoyant weight gamma W into 4 by 3 pi into d by 2 whole cube. Now I will put this particular portion on the left hand side, and what you will get guys exactly, this is basically gamma S. So we can take out the common which is nothing as 4 by 3 pi d by 2 whole cube, and this is nothing as gamma S minus gamma W, and it should be equal to how much? Half CD rho W into AP into Vs square. Now Vs is what? Basically Vs is nothing as your settling velocity of particle, which is basically a constant velocity. Settling velocity. Clear? Okay sir. Now just check it out guys. Can I write this particular thing 4 by 3 pi d cube divided by how much? 8, and we can take out the rho W as a common, and it will be G minus 1, and it should be equal to how much? Half CD rho W. Now what is AP? AP is nothing as, that is basically the projected area. Now you can see here guys how much projected area we have. Pi by 4 into d square. So you need to write pi by 4 d square multiply by Vs square. Correct? Now you can see here guys, we can cancel rho W and rho W. This d square and this will be d. 2 into 4 8, and this 8 will cancel. Any other thing? Any other thing? Any other thing? Pi and pi. Okay. So the equation will become 4 by 3 G in minus 1 into d upon CD is equal to Vs square. So Vs is equal to under root of 4 by 3 G minus 1 G minus 1 to small g also, small g into d divided by CD, and this is your final equation, right? Because we have written it as a rho means gamma S, right? This is gamma S. So we need to convert it in terms of density, right? This is a specific weight. So we need to convert it into the density. So rho W into G, small g also. Understood? So this is the general expression guys, which is basically nothing as the settling velocity of a particle in general. So if you change the size of particle, then definitely the settling velocity formula will also get changed. So let's understand what is that. So guys, it is very simple. You need to draw one table. First, I wish to write the type of or size of particle, then type of flow, size of particle, then type of flow, Reynolds number, which is nothing as Re, and I think all of you know that, rho Vd by mu, clear, and then Cd value, which is nothing as drag coefficient. Now guys, let us suppose if the size of particle is greater than less than 0.1 mm, let us suppose if the size of particle is less than 0.1 mm, then what should be the value of drag coefficient? Less than 0.1 mm. So the flow will become basically laminar flow, and Reynolds number is less than 0.5. Reynolds number is less than 0.5. So the drag coefficient is nothing as it is 24 by Re. 24 by Re. Please remember this value. Second condition, let us suppose if you change the size of particle, it is in between 0.1 mm to 1 mm. And the flow which will become over here is transition flow, and the Reynolds number is greater than 0.5 in this case, and it should be less than 10 raised to power 4. So this particular formula of CD will become 24 by Re plus 3 by root Re plus 0.34, and this is nothing as basically the transition flow. And the last case, which is basically the size of particle is greater than 1 mm, in that case the flow will become turbulent flow, right? And the value of Re will become greater than 10 raised to power 4. In that particular case, CD is equal to 0.4 directly. Clear? Now guys, you need to understand which particular type of flow you have to consider in case of water treatment plant, and which type of flow you have to consider in case of wastewater treatment plant. So guys, let me explain it. Most of the time in case of water treatment plant, you may find the laminar type of flow only, right? But if you have wastewater treatment plant, all the three type of flow you may see in the different treatment unit, right? Like grid chamber and etc. So that's why guys, all three law is important for wastewater treatment plant, but the laminar flow is important for the water treatment. Clear? Now, if you use the laminar condition when the size of particle is less than 0.1 mm and the Reynolds number is less than 0.5, so that particular law is nothing as your Stokes law. Stokes law. Clear? Now guys, we will try to derive the Stokes law, and then you are able to understand the final equation over here. Then we'll discuss the problem portion. Okay, listen. So as per Stokes law, the value of CD is equal to what? 24 by Re. Correct? Now you can see here guys, Stokes law is valid only when the size of particle is less than 0.1 mm and the flow should be laminar and the Reynolds number is less than 0.5. Then only you can apply it, otherwise not. Okay. So CD is equal to 24 by Re. So what was our formula to find out the settling velocity? Vs square is equal to 4 by 3 G minus 1 into G into D upon CD. Correct? So can I write here guys, Vs square is equal to 4 by 3 into G minus 1 into G into D. Now what is the value of CD? It is 24 by Re. How you can write 24 by Re? 24 by rho Vd by mu. So if you divide it by mu, so it will come in the numerator part. Put it. So 24 into mu multiply by rho W Vs into D. You can cancel this one. Okay. Any other thing? No sir. You can cancel this one also. It will become 6. So ultimate formula will become Vs is equal to 1 by 18 mu bracket G minus 1 into rho W into G into d square, right? So this is nothing as, this is basically our Stokes law. This is nothing as, this is our Stokes law. Getting it? This is nothing as, this is our Stokes law. Now guys, you can see here, if I want to change it in terms of kinematic viscosity, how you can write it? You know that guys, the value of dynamic viscosity divided by density of water is written as kinematic viscosity. So you can convert this particular expression in terms of kinematic viscosity also. So we can write here settling velocity is equal to 1 by, you can divide mu by rho w. So ultimately it will become nu, kinematic viscosity, bracket g minus 1 into g into d square. So this is another way by which we can represent the Stokes law. Getting it? Crystal clear to all of you guys? Crystal clear to all of you? Any doubt in this case? Any doubt in this case? Crystal clear to all of you? Yes or no? Please write in the chat box guys so that I can understand. Crystal clear? All of you are able to understand this expression? Very nice. Very nice. Now tell me guys, now tell me quickly, the settling velocity of particle will depend upon dynamic viscosity. As per the expression, you are able to see this. As per the expression, the settling velocity of particle is depending upon the density as well as the viscosity of fluid. You can see here guys, it is inversely proportional to the viscosity part. If you have more viscous or more viscosity in the fluid, then the settling velocity of particle will be lesser. Correct? Now the second thing is the density of particle. You can see here guys, g into rho w is nothing as basically our g into rho w into small g is nothing as our specific weight of particle. Now tell me guys, if you have more specific weight of particle, or either you can write g is more, then can I say that the settling velocity will be more? Yes, yes. Similarly, you can see here the settling velocity is proportional to d square. That means if you have greater size of particle, then the settling velocity of particle will be more. Crystal clear? I think it is clear to all of you, right? So all three conditions you are able to see here guys, which we have discussed already in our starting of the session. Getting it? Okay. So let's do the quickly over here guys some problem. Okay, then we'll close the session. Tell me the answer of this. First question in front of you. First question in front of you. If the specific gravity of suspended particle is increased from 2 to 3, then the settling velocity will be. Tell me guys quickly. If the specific gravity is changing from 2 to 3, right? It is changing from 2 to 3. Then what will change occur in case of settling velocity of particle? Which particular answer is correct? B, get doubled. Okay, very nice. Very nice, Prem. Very simple question. You know that guys, Vs is equal to what? 1 by 18 mu bracket g minus 1 into gamma w into d square. Now guys, let us suppose in the initial condition, the value of g is equal to how much? The value of g is equal to 2. Let us suppose g is equal to 2. If you consider g is equal to 2, then the settling velocity of particle, let us consider Vs1, it is equal to 1 by 18 mu 2 minus 1 gamma w into d square. So you can write it down like a gamma w into d square divided by 18 mu. This is nothing as Vs1. Now guys, if I consider g is equal to 3, then the value of Vs2 is equal to how much? 1 by 18 mu 3 minus 1 into gamma w into d square. So you can see here guys, it is twice of gamma w d square divided by 18 mu. And what is this value? This value is nothing as basically Vs1. Correct? So you can see here guys, our velocity is changing and it will become double as compared to the first condition. And that's why B is the correct answer. B is the correct answer. Next question. Tell me the correct answer. So we have two statements. One is assertion and second is reason. Okay. Please read it very carefully guys. And let me tell you how to approach this type of question also. Listen. don't try to relate the statement in the first step. Okay, what you need to do, listen carefully guys. Basically we have 4 options, A, B, C, D, correct? Now guys, there are 2 conditions first which we need to check. The assertion part can be true or can be false. The reason part can be true or can be false. Okay, okay sir. Let us suppose if assertion is true, assertion is true, okay, assertion is true, and let us consider at the same time the reason is false, reason is wrong. So guys, you will get your answer directly without matching or without trying to link the statement, both the statement together. Okay, so the first condition, if reason is wrong, then definitely the answer is what? The answer is C. Now let us suppose guys, if we are getting another condition in which the assertion is wrong and the reason is true. So guys, the answer is what? D. So in the first step, just you need to check whether the assertion is true or reason is true or false. You need to check that condition only first. Okay. If you get any statement as a wrong, then you will get your answer. You don't have to check again guys for the option A and option B. Now let us suppose guys, anyhow both the statement are true. That means assertion is true and reason is also true. Now in this particular case, you need to put a word because. Okay, try to use a word because. Use a word because and insert it between these 2 statements and read this particular 2 statement completely as a single paragraph, right? If you get a feeling, yes, it is the correct reason for the assertion portion, then the answer will be A. If it is not correct, the statement correct reason for the assertion portion, then it is B. Then it is B. Understood? So this should be the approach which you have to follow in case of assertion and reason questions. Let's understand. The settling velocity of a discrete particle will become 5 times when the dia is double. Guys, we know that the assertion is itself is wrong and we are getting our answer. We know that Vs is proportional to d square. If you make it double, then the settling velocity will become 4 times, nothing else. Clear? Not 5 times. That's why D is the correct answer, because assertion itself is wrong answer. Clear? And you can see here guys, the reason is right. Why? The settling velocity of a discrete particle is almost proportional to the square of the particle dia. Clear? Okay. Next question, which is nothing as basically a MSQ. Guys, this is a MSQ type of question in which multiple answer can be correct. So you need to check which of the following questions or which of the following statements are correct in this particular case. Okay, please solve it and check out which particular statement is correct and which statement is wrong. Listen guys, what they have given: the spherical suspended particle having a radius of 0.02 mm. Let us suppose the radius is 0.02 mm. If you convert it in terms of dia, it will become how much? 0.04 mm. Okay sir. The specific gravity of particle is equal to how much? 3.0. And it need to be separated in the settling chamber, and the value of small g is also given, which is 9.81, and the density of liquid is also given, and the viscosity is given as kinematic viscosity 10⁻⁻⁶ meter square per second. Clear? These are the data which is given to us. Okay, now let's check it out guys, which of those statements are correct over here. Okay, let's see. First thing, we need to find out the settling velocity of particle. Okay, so you know that what is the formula? Vs is equal to how much? 1 by 18 nu into g minus 1 into small g into d square. Clear? Now 1 by 18 nu, nu means kinematic viscosity 10⁻⁻⁶, bracket g is 3 minus 1, small g is 9.81 multiplied by d square. D is how much? 0.04. So guys, 0.04 multiplied by 10⁻⁻3, because I want to convert the mm into meter part and put it square. You will get your answer. Vs is equal to how much? Tell me guys quickly. Vs is equal to how much? How much you are getting? Please let me know guys. what will be the answer after solving this thing? How much you are getting, guys? 1.744 into 10 raised to power minus 3 meter per second, or either we can say that 1.744 mm per second. Correct? Yes or no? Tell me, guys, quickly. This is the settling velocity which we are getting in this particular case, 1.744 mm per second. $1.744 per second. Yes or no? Okay, so this is nothing as basically your settling velocity. Now tell me, guys, any of the answer is correct or not? A and B are wrong. Both the statement are wrong. A and B both are wrong, right? Because as per their statement, the velocity should be 0.436 mm per second and 0.436 centimeter per second. Clear? Next case. Now tell me, guys, if the specific gravity of particle is reduced from 3 to 2, then the settling velocity is reduced by 50% or not? That is the question. Tell me, guys. Let us suppose, okay, let me write here. Tell me, guys, if the settling velocity, this statement is correct or not, please let me know, guys. If you write 1 by 18 mu bracket g minus 1 into g into d square. Now tell me, guys, if you reduce this particular value of g from 3 to 2, then the settling velocity of particle is reduced by half or not? Yes or no? Tell me, guys, quickly. It will get reduced by 50% or not? That is the question. The velocity will get reduced by 50% or not in general? Arey Baba, we have already discussed the same problem earlier also, right? You can see here, guys. Tell me, if you put 3 over here, right? If you put 3, g is equal to 3, then the settling velocity is vs1, and that velocity is twice of g into d square upon 18 times of kinematic viscosity. Now, if I put g is equal to 2, what should be the settling velocity in this case? So, it should be equal to how much? It should be equal to small g into d square upon 18 mu. Now, tell me, guys, initially it is twice, now it is half. So, can I say that yes, it is reduced by 50%? Correct? So, this statement is correct. Okay. Now, the next statement, if particle is less than 0.1 mm, then Stokes law is valid. Yes, it is also correct. So, C and D are the correct option, A and B are wrong one. And that's why, guys, only 2 options are correct, because this is a MSQ problem. Crystal clear? Okay. Now, let's move to the last question, guys, which is basically based upon to find out the size of particle in this particular case. Now, there is one more terminology which is known as surface overflow rate. Now, the question is, what it is, sir, exactly? Okay, that is your question. Okay, listen, guys. What is surface overflow rate? First, we need to understand that. So, guys, let us suppose this is your sedimentation tank. If you pour the water in it, then what will happen? The water is trying to move in upward direction. If you pour the water, then water is trying to move in upward direction. Clear? That means what? This is nothing as the rate by which water is trying to come out of the tank is known as surface overflow rate. So, guys, this is nothing as surface overflow rate, by which, or you can say that the rate by which water is trying to come out of the tank or coming out of the tank. So, this is nothing as, this is basically given as 30 meter cube per day per meter square. Now, the formula for surface overflow rate and the settling velocity of particle is same, and that's why if the data is not given for the settling velocity, you can consider the surface overflow rate as a settling velocity itself, or design settling velocity. Let me show you that. This surface overflow rate is nothing as the discharge which is coming out of the tank, and this is your surface area, correct, which is nothing as AS. So can I write here, guys, surface overflow rate is equal to Q by AS. Simple. Now at the same time, what is the design setting velocity in this case? Let us suppose this is a design particle which is trying to settle down in the tank by Vs. So you can write here, guys, Vs is equal to Q by surface area. You can see here, guys, both the formula are same, but the terminology are different. That means the definition are different. So we can use the settling velocity or design setting velocity as surface overflow rate also. Please remember this point. If data is not given, then SOR can be considered as design settling velocity. Clear? Now guys, let's solve this particular problem to find out the size of particle, and which is very simple. Okay. So guys, can I write here Vs is equal to what? Again 1 by 18 mu into G minus 1 into rho W into G into D square. Now guys, this particular value of Vs is given as in terms of surface overflow rate. So you can see here it is basically 30. So this value is in 30 meter cube per day per meter square. You can solve it. So let's convert it in terms of meter per second. 24 into 3600. 1 by 18 mu. What is the value of mu? It is given as 0.001. Bracket G. G is equal to how much? 2.65. Minus 1. Multiply by rho W is 1000. Small g, which is 9.81. And you need to find out the size of particle, which is basically D. Okay. Let's do it and find out the size, and please let me know the answer. So guys, we are getting an answer of D is equal to 1.965 into 10 raised to power minus 5 meter. If I convert it in terms of mm, then how much it is? Multiply by it 1000. Okay. So in terms of mm, it is equal to 0.0196 mm. So you can equate it with respect to 0.02 mm. Clear? So this means B is the correct answer. This means B is the correct answer. Tell me guys, this 0.02 mm is the correct answer. Clear? That means B is the correct answer. Understood? Crystal clear to all of you guys? Crystal clear to all of you? Okay. So that's it guys from my side for today. And I hope you are able to understand the complete concept of sedimentation analysis. And these expressions will be very useful in case of WTP as well as in case of STP also. So please watch this particular video completely guys, and try to understand how to derive the expression completely and how we can use it in different conditions. Okay. So guys, again tomorrow we will have one more session in which we will discuss one more important parameter of environmental engineering at the same timing, which is 8:30 p.m. Okay, let's meet tomorrow guys, and kindly share this particular session to other students also, and subscribe our channel and hit the like button as well as hit the bell icon also, so that you will get the notification. Any query if you have guys, please let me know. I wish to explain it or I wish to clear it. Otherwise we will close the session and we will meet tomorrow. Any query guys from your side, you can ask me anything. Okay, so let's close the session guys, and let's meet tomorrow at the same time. Bye. Take care guys. Thank you so much.